Quantum computers sound like magic, but the real question is not whether they are powerful. The real question is what kind of problem they are powerful for. A classical computer and a quantum computer are not just faster and slower versions of the same machine. They are different tools. One is built for clear, reliable steps. The other is built to use the strange rules of quantum physics for certain special calculations. The computer in your phone, laptop, car, game console, and bank server is classical. It stores information as bits. A bit is simple. It is either 0 or 1. Every app, website, image, and video is ultimately built from huge patterns of these tiny choices. Classical computers work so well because bits are easy to control. A tiny switch is on or off. A voltage is high or low. Even if the hardware is unbelievably small, the goal is still to make each decision clear, repeatable, and reliable. Classical computing is built from logic gates. A gate takes bits in, follows a rule, and produces bits out. Chain enough gates together and you can add numbers, open a browser, edit a photo, or train an AI model. This step-by-step style is incredibly powerful. Classical machines are fast, cheap, stable, and easy to copy. They are also very good at moving data, storing data, displaying results, and running the everyday software that modern life depends on. But some problems grow in a painful way. When the input gets a little larger, the number of possible answers can explode. A classical computer may still follow the rules perfectly, but the path can become far too long to finish in a useful time. A quantum computer uses qubits. A qubit is not just a tiny classical bit. It is a physical quantum system such as an atom, ion, photon, or artificial circuit, controlled carefully enough to carry quantum information. The famous idea is superposition. People often say a qubit can be 0 and 1 at the same time. That phrase is helpful, but incomplete. A better picture is that the qubit has a mix of possibilities, with each possibility carrying a size and a phase. When you measure a qubit, you do not see the whole hidden mixture. You get a normal answer, such as 0 or 1. The art of quantum computing is to shape the mixture before measurement, so the answer you want becomes more likely to appear. This is where many explanations go wrong. A quantum computer is not simply trying every answer at once and then handing you the best one. If it were that easy, almost every hard problem would be solved. The real power comes from interference. Interference means possibilities can add together or cancel out, much like waves in water. A quantum algorithm tries to make wrong paths cancel and useful paths reinforce. That is very different from a classical search through a giant list. Another key idea is entanglement. When qubits are entangled, you cannot fully describe each one separately. Their states are connected as one larger system. This lets a quantum computer represent certain patterns in a compact and deeply linked way. The promise of quantum computing is not better spreadsheets or faster video calls. The promise is that nature itself is quantum. Molecules, materials, and tiny particles follow quantum rules. A machine that also follows quantum rules may simulate them more naturally. Imagine trying to describe ocean waves using only square blocks. You can do it with enough blocks, but it gets messy. Now imagine using waves to describe waves. For some problems in chemistry and material science, quantum computers may offer that kind of natural fit. If this kind of clear tech explanation helps, consider subscribing. We are going to keep separating real future technology from hype, one concept at a time. Now let us look at where quantum computers actually help, and where they probably do not. The strongest use cases are narrow but important. Quantum computers may help with simulating quantum systems, studying molecules, improving some optimization methods, and running special algorithms that change how certain math problems scale. One famous example is factoring very large numbers. Some public key cryptography relies on the fact that classical computers struggle to reverse certain math problems at huge sizes. A large, error-corrected quantum computer could threaten some of those systems. That does not mean today's passwords suddenly vanish. It means security systems need to plan ahead. Researchers and standards groups work on post-quantum cryptography because the responsible move is to upgrade before powerful quantum machines arrive. Another famous idea is quantum search. For some unstructured search problems, a quantum algorithm can reduce the number of tries needed, but it does not turn every impossible search into an instant answer. The improvement is real, but not magical. Optimization is often mentioned in quantum discussions. This means choosing the best option from many possible options, like schedules, routes, or designs. Quantum methods may help some versions, but optimization is a huge category, and many cases remain better suited to classical methods. For normal computing, quantum is usually the wrong tool. Writing documents, streaming movies, hosting websites, running phone apps, and storing photos do not need quantum behavior. Classical computers already do these tasks extremely well. Quantum computers also do not magically swallow massive databases. Getting ordinary data into a quantum state can be difficult. If the input and output are mostly classical data, the time spent loading and reading information can erase any possible advantage. A quantum computer may hold a rich internal state, but measurement gives only a limited classical result. You cannot directly print out every possibility inside the machine. A good quantum algorithm must be designed so a small number of measurements reveal something useful. Qubits are delicate. Heat, vibration, stray fields, and unwanted interactions with the environment can disturb them. This loss of quantum behavior is called decoherence. It is one reason quantum hardware often needs extreme isolation and careful control. Classical computers have errors too, but they are usually rare and controlled. Quantum errors are trickier because qubits can drift in more ways than just flipping from 0 to 1. Protecting quantum information requires special error correction techniques. This leads to an important distinction. A physical qubit is one real hardware qubit. A logical qubit is a protected qubit made from many physical qubits working together. For large, useful algorithms, logical qubits matter far more than raw qubit counts. Some quantum computers operate at extremely low temperatures. Others use trapped atoms, ions, photons, or different physical systems. Each approach has trade-offs in stability, control, scaling, and manufacturing. There is no single perfect design yet. In practice, quantum computers are usually paired with classical computers. The classical machine prepares the problem, sends instructions, collects measurements, and adjusts the next steps. The quantum processor acts more like a specialized accelerator than a replacement for the whole computer. A helpful comparison is a graphics card. A GPU does not replace your laptop's main processor. It accelerates certain workloads, especially parallel math for graphics and AI. A quantum processor may play a similar role for certain quantum-friendly problems. Hardware alone is not enough. A quantum advantage needs the right algorithm, the right problem structure, and enough error control. If the problem does not match quantum strengths, a quantum computer may be slower, noisier, and more expensive than a classical one. Another reason to be careful is that classical computing does not stand still. Better chips, better algorithms, cloud systems, and specialized accelerators keep raising the bar. To be useful, a quantum approach must beat the best classical approach, not a weak comparison. The biggest misunderstanding is thinking quantum means automatically faster. It does not. Quantum computers are not upgraded laptops. They are experimental and specialized machines built to exploit superposition, entanglement, and interference for carefully chosen tasks. A better mental model is this. Classical computers are universal workhorses. Quantum computers are potential scientific instruments and accelerators for problems where quantum structure matters. The future is less about one replacing the other and more about both working together. When you hear a quantum computing claim, ask a few simple questions. What problem is being solved? What is the classical baseline? Are errors corrected? Is the result useful outside a lab demonstration? These questions cut through most of the noise. Classical computers turn clear bits into reliable steps. Quantum computers shape fragile possibilities so useful answers become more likely. That difference is the whole story. Quantum is not magic, and it is not useless. It is a new kind of tool for a special class of problems. What part of quantum computing still feels confusing to you? Superposition, entanglement, error correction, or the real-world use cases? Ask your question in the comments or suggest the next future technology topic you want explained in plain English.